Hey class, it's Professor Nick Sensky at UNC Charlotte, and this is a tutorial video for week 5 of computational methods. And the topic this week is parametric design process. And by this I mean the process of designing a parametric system. Like, how do you go about making a system so that you can make an artifact that's computational, like this wall by Gramazio and Kohler. Okay, this is something that you could design by hand, but it'd take you much longer to do that. And computationally, if you have a system, it allows you to play with it, to experiment with it, to make changes to it and vary it, so that once you have the idea. You can go through different variations of it and decide what you want. Okay, so how do you make a tool essentially that allows you to explore a design space like this? Okay, so what I'm going to be talking about today is sort of like three-dimensional topology. And what I mean by topology is what 3D forms are constructed from. Okay, so you see something in the computer, and the final form of something, let's say, would be like this box. Okay, and we look at it and we see the box, and we think that that's kind of all there is. Like, you have a form, it's in the world, it's a solid. You could build this, you could dimension it, you could draw a set of drawings for it that someone could use to build it. And again, this is just kind of an analogy, but so we think of things like this, but in fact, in the computer, right, this box is actually made up of surfaces. So if I explode the box, it's actually a collection of 6 surfaces. Okay, I could take one of those surfaces, and that surface is actually made up of edges. So I'm duplicating the edges and I'm exploding. So there's 4 curves that make up that box. And for each one of these, right, there's actually a point. And so everything goes back to points, which is why I'm so sort of like hung up on those in a class, right? A point is defined by a set of coordinates in space, which are just basically numbers, right? And computation is really about figuring out specific sequences and amounts of numbers. Okay, and so if you have numbers, you have points. You have points, you can generate a line. If you have lines, you can generate a surface. And you have multiple surfaces, you can generate a solid, okay, a form. And so you have to really bear this in mind when you're working. It's like because sometimes you want to take a form that you already have, that's something that you modeled in Rhino, and break it down so that you can get access to curves on that surface, and then use those curves to find points, and then use those points to distribute some geometry. Or start from a series of like points and work your way all the way up to your final form. Okay, and sometimes during the course of designing something parametrically, you'll go back and forth through these different forms. Okay, you'll find some curves and make points. Use those points to make different curves. Use those curves to make a surface. Okay, so just bear in mind the mutability, the flexibility of 3D geometry. Okay. And this is something that doesn't just pertain to Rhinoceros. This is something that, like any 3D software, everything, all the way from AutoCAD to Maya, Studio Max, these are the general principles of how these programs work. So, do not get stuck in this thinking that this is just a Rhinoceros idea or even a grasshopper idea. This is fundamentally how things are created in 3D, no matter what you use, okay? If you're using CATIA with Frank Gehry, you're still operating in this kind of environment. Okay, 3D topology. Okay, not So anyway, this is a really important idea when you begin thinking about like a project like this and how you might go about making it. Okay, you look at this project, you know that it's essentially a distribution. Like you have a brick, and a brick is distributed in some way. There's many bricks here, right? There's a network of bricks, okay? And so your question should be two things. Is like one, okay, I need to make that brick somehow, which could be very basic. It could be just a center box. But then two, the harder question, how do I distribute that brick in that way so that I get the form that I'm looking at, okay? And so that's what we're going to be talking about today. But before we do that, I need to introduce two more patterns that we haven't talked about before in class, okay? I promise I'm going to stop giving you these things, and we'll just focus on putting the pieces together this week. But I do want to give you two more things that are very valuable that show up a lot in these computational design projects, okay? And let's go ahead and look at that. So I'm going to go ahead, and I've got Grasshopper fired up, and I am going to go ahead and start with, actually I'm going to go ahead and make a shape, and then I'm going to go ahead and explode this. And I'm only doing this to kind of speed things along here. I don't expect you to, have to do this, but so we have a surface, and I've shown you lots of different ways to generate surfaces, right? And the ways that we looked at have really revolved around lofting, but there's also, you can make surfaces out of points. Anyway, so let's assume that you have a surface, okay? And you can take that surface and you can get the basically section curves out of it. So you can take a surface and you can get curves. And so let's go ahead. In this case, I'm going to make a surface container, and then what I want to do is drop a contour object, if I can spell contour correctly. Contour, okay? And contours take actually I got the wrong, that's not right. Let's go into, it's under the intersect panel, and I want to look at contour. There we go. You gotta get the right contour here. Okay, so we're gonna look at, it says brep or mesh. Okay, brep is boundary representation, and if you look at the upper right hand corner, it's geometry. You don't have to worry about the kind of Rhino language. A boundary representation could be a surface. It can be a solid. It's fine. It's the bounds of an object. In this case, it's the surface. And we're going to reference that surface by saying set1 surface, and then I can go ahead and hide this. Okay. And then you've got a start point, and you've got a direction, which is x, y, or z vector, or an arbitrary vector, and the distance between the contours. So distance is a number, and in this case, I just want to do a number slider, and I'm gonna give it a little bit more of a value here. And we need a start point. In this case, I'm going to chicken out, and I am just going to use the XY plane as a start point because this is sitting here on the default. We'll talk a little bit more about this later, but we're going to do that. Whoa, we have a lot of contours. Let's dial it down a bit. If we increase the distance, we get fewer contours. Right? More distance, fewer contours. And let's see here, yeah. And the contour direction defaults to Z, that's what we want. We could do it in a different direction. I'll just throw out an X vector. And then you can see we actually cut, I'll turn the surface off here to show you. We actually cut contours this way. Okay. And the result of this are you have 69 contours, curves. Okay. Notice that they're grouped. That's because if you have an object and you happen to cut something, and they're like right now it's pretty easy because this form is not doing anything funky. But if we had like a camel hump if we cut that, we'd end up with 2 curves instead of 1, and so they stay grouped. Okay, so keep this in mind. These are already grafted, so you might need to do some ungrafting. Okay, to get back to the original idea, though, I deleted my surface. There we go. We're interested in this z direction here. This is essentially like one of these chipboard models, like a site model, right? But you're cutting up a surface, and you get curves from it. Okay, and this could be really useful. Go ahead and do that. If you have something, let's say that you already lofted. So this is actually a pretty common usage. So if I go ahead and let's assume that that is a parametric loft, right? So any surface that we have, we can create the contours from. Okay. So so that actually makes this pretty useful for us. So we take a surface and we can get curves from it. This is going to be helpful with our wall example, right? Because we can see how each of these is kind of a band, there's a curve, and remember with things like divide curve or curve length, we can basically put points along a curve, and once you have points, you can distribute geometry, right? We can distribute things like our bricks. Okay, and so you could look at this and you'd say, well, okay, I'm pretty far along here. Like I have this idea for this wall. Let's go ahead and say divide curve. Let's just put a divide curve in there. And I'm going to go ahead and we're going to need a lot of bricks. Let's call this number of bricks. Okay, and plug it in and make a lot of them. And then plug this in for the amount, number of segments, and plug our curves in. And we get a whole mess of points. And I'm going to go ahead and flatten these. Doesn't really matter in this case, but I like not having them grouped. They don't really need to be grouped. Okay, so I've got a whole mess of points here. Okay, and I can keep adding, contours. And then I could go in and I could say, oh, well, those are basically just center boxes, right? Like for bricks, I'll plug in a box. Ooh, pretty good there. And let's go ahead and turn off those points for now. And let's put in some number sliders. Just kind of play with these. Oh, that's pretty good. Actually, that already is pretty good. Let's turn these off. These are just the curves I used to make the loft originally. But let's look at that. Oh, but look at this though. These bricks are rotating in line with the curve, and that's a problem. Like ours are all aligned the same way. And you can say, okay, so let's look back. We've done something pretty successful here. We got these things kind of stacked up. We have that idea going, like we can control it parametrically, but they're not rotated. So we're missing something here. Like we can distribute these things, but they don't follow the curve. And we could go in and we could put in some rotate components, and we could try to like rotate them. But what happens if we change the curve? Because we're going to need to do that anyway, because this isn't the same as that. We need to make this curve. And it's probably going to involve something. It's going to vary as it goes through here. It's really complicated. But I have a solution for this. Okay, instead of a divide curve, we are going to use something else. Go ahead and hide the box here. We are going to use I'm going to make fewer of these here. We're going to go into curve and use a horizontal frame. And there's horizontal frames and there's perpendicular frames. And the horizontal frame is really useful I'm going to go ahead and I'm just going to put a curve container in here and reference my original curve just for the sake of visualizing this. So I have a curve, and you have n number of segments. So actually I can go ahead and plug this back in. And you get these frames, and if you know, there's a kind of confusing, but if you look at it, frame, if you look in the upper right hand corner, a frame is just a plane. And we know that planes are places where you can distribute geometry. So if I take something like cylinder, you can place them, you know, right? This is the base plane, and I get my things, and they were going to go along. And you'd say, Nick, that's really lame because this looks just like the divide curve example, only there's all these, you know, sort of like coordinate planes, but you haven't really done anything different. But actually, I have, because the planes have an alignment, and that alignment is changing, it's shifting with the curvature. Okay? And this is different when you have something that has a grain to it. If you plug in the box, and if you unhide the box so you can see it, let's turn preview on. Okay, check that out. See, they are actually flowing with it. Okay. So the frames, the horizontal frames, is really useful for this kind of thing. And there's perpendicular frames, and you can do perpendicular frames, which is the same idea. It's going to adjust with the flow, only the planes that it generates are perpendicular to it. So it's really great for sort of like a horizontal loft kind of form. If you want to rotate a cross section through something, you can experiment with that later. But the horizontal frames is something I haven't talked about, but it's essentially a way, it's a special way of getting planes along a curve. And I haven't talked about it, and that's really key for certain types of distribution problems. And now we're even closer to this idea of the brick flowing along the wall. Okay. So then the next piece of this is that we're going to go ahead and take this, and I'm going to disconnect that curve and reconnect my contours. And then I get this. I'm going to hide that curve. So we are even closer. Okay. There is a problem though. So spacing's okay, but there's gaps in these things. Okay. And I can go through and I can kind of play with this contour here, and I can see, like, we want the brick to sit on top of the other row of bricks, right? As close as you possibly can. And you can say, well, that's pretty good. And you might do this and then kind of call it a day. Like, you might say, okay, now they're on top of each other. Like, mission accomplished. You know, they're very close to having the right spacing. Okay. But if we're doing a parametric system, that might not satisfy us. It's like, what if I go in and I change, and I need to actually change, this is going to be the brick length. That are labels. And let's make this the brick height. And what if I plug this in for the height? It really messes up my spacing now. Oh, it's terrible. Okay. Ideally, you'd want some relationship between the contour distance and the size of each brick. Okay. And remember, these are center boxes, right? So this is kind of a radius. And so you could look at this. Now let's go through, and so we know, let's put this on a known value. Let's say that the heights are 1. Okay. And if the heights are 1, this is like 1.18. Let's try like 2. I mean, you can do this experimentally, but there you go, exactly. So the relationship is essentially that since this is a radius, right, the size of the brick is 2 times this. It's a 2-unit high brick. That means the distance for each contour needs to be 2. Okay? But if you look, the way we have it, we kind of have this contour distance here. That's kind of the way that the thing's set up. Okay? So we do this 2 different ways. And I think, though, what we want to do is base it on the unit. So what I want to do is take the brick height, and I want to take a multiplication, and I'm going to extract the parameter and make this 2. And let me just make sure that 2. Okay. So I get value, and then I'll plug that in. Because I don't really care about the distance of it. I really care about, this is a modular system. I care about the unit that I'm working with. Okay. Okay, and so now I've got the brick, and I've got the height, and let's play with it, and you can see that it's perfect. Like, I have no gaps. Like, the bricks touch each other. Okay. And there's something else wrong with it, though. There's not really, these are just towers of bricks. There's no coursing, there's no running bond in this, right? So I would ask myself, how do I make that shift, right? And I would say, where have I seen a pattern like that before? Like, where have I seen something that there's one row that's doing something, and then the row next to it is doing something else, right? You think back to those color patterns that we looked at, right? And the checkerboard, and how I could do like circle, square, and then the next row would be shifted. So this is an example of saying, okay, I've got my distribution, like I have my original form. Let's just go all the way back here. Got my form, which I use to give me my lines, my curves, which gives me my distribution points, all these crazy planes here. And then I distribute my geometry. So now I have all this stuff. And then I can apply, patterns to it, right? Like I could transform it. I could shift each brick with move, or I could rotate them in strange ways, like again, or I could change the scale of them slightly, or I could apply a pattern, like a cull pattern. And that's what I'm going to do. I'm going to do cull nth. I plug it in, and I'm going to cull every other one. And remember, cull doesn't really show up until you turn off preview. Okay, I did something, and it's not really what I want. What is the problem with this? Well, if I look at my data structure, remember with cull, if something is grafted and you cull it, it's only going to cull like rows. So it's culling every other stack of these. Okay, in order to get at that, to get that shifting, to get the checkerboard, I need to flatten the data structure. Right? So then if I have access to each one of these, then the call frequency can take over. And you say, oh, Nick, it didn't work. But if you look at this, it actually only works with even numbers. Right? Because if you have an odd number, the rows align with each other, and essentially you're not getting any effect. Okay? So again, to make a successful kind of checkerboard pattern, you have to have an even number of objects in each row to make sure that you flatten things. And then you can apply the cull n pattern with a value of 2. Okay? So there's a way we can force this to be evens, right? You can right-click it and go and edit, and then you can say even numbers only. If you had a different one that only worked with odds, you could say odd numbers only. And now, if I'm doing this, every time I do it, it's always going to work. And now I've adjusted it slightly, and the spacing's even better. So now I'm like even closer to my Grammatio and Kohler wall, because I figured out this was the question that I asked you guys in homework, right? How does this cull pattern work? The cull pattern works by removing every other one, and then if you change the spacing enough, so it's a checkerboard with smaller spacing that creates the running bond pattern. Okay. And what it does also, which you may not care for, is it does give you this kind of shift at the end. But this is right. This would work structurally. You lay one brick on top of the other. They're roughly the loads going through the brick in the right way. You can see there, like a line of force going through there. This would stand up with a bit of transparency, right? Pretty nice. Okay, so not bad. So went from points, and then we distributed, and then we applied some logic. So this is a very general pattern for computational design process. Okay. And the last step is to take our process that we have, that we figured out, and look at our final form. And we had this process, and remember we started off with a surface. And so the question that we would have now is like we could take a step back and say, okay, how do I get this surface? Like I have the method, like I make these bricks and they have the right spacing and they adjust to the flow of these lines. But I got to go back to this original surface. And I need to make this better. This is the one that I drew. Right? I drew this surface. And that's a valid technique, right? Like I could have a model of a building that I made that has a wall in it. Like let's just do this like arbitrarily here. Talk about this later, but this is actually this is actually what I want you guys to learn is if you have a Rhino model that you've made for class, and let's just say that this box represents your building. Okay. I'm going to explode this. You could take a surface of that building and essentially set that surface. And then you would get, if I hide this, I'll hide my old one too. This is now part of, this could be part of your project. And I'd have to go in and I'd have to adjust the spacing of it. Should probably need more. But any arbitrary wall could become the surface that you use. Okay. That's pretty powerful. You just take anything that I draw and I can say, okay, take that surface and set it. And now that top one's not going to work for a different reason, but yeah, that one works. Okay. We'll look at why that doesn't work later, but basically because we're contouring a surface vertically. Okay. But check that out though. How cool is that? I mean, you can even go in and set multiple surfaces. And you bake this, and it's going to take a little bit. And let's hide this. And that's a Rhino model. Like that is your building. Okay. So this is a process that you could use in your own projects once you have this kind of system established. Okay. But that's not the Gramazio and Kohler wall, right? We need to get a specific surface that looks like this so that we can get the contours and then get the bricks on them. So how would you make that? Well, if you look at this, it's essentially this kind of mathematical, in-out kind of sine curve. And we know how to do that. We just did that like last week, right? We can make curves. And if we took those curves and we lofted them together, we would get this surface. So let's take a look at that. Let's see how we would do that. Let's just start raw. And remember how we do this? This is a pattern that we use all the time. Take a series and some points. And we start by plugging in some points. And I'm actually just going to go ahead and say number of points. Oops, it's actually this. And let's say number slider. And this one's going to be spacing. And the values are going to be 0 to 5. Okay, so I have lots of points. I don't really need that many points. And some pretty decent spacing between them. Then the other bit that we did was to play with the y value. Remember the x value. And if we use a graph mapper to vary the y value, we get these interesting mathematical curves. And to do that, we put a range in, and the range is always one less than the other series that we put in, so n minus 1. You know, this is something that we've done so many times. This pattern should be ingrained in you. We have a series value and a range value that varies, and we plug these in for a point. Okay. Remember, with our graph mapper pattern, we also need some kind of a multiplier, because the values that come out of it are very low. So I'm just going to say 20. Plug in for y, and I don't have any value in there, so I'm going to do a sine curve. Okay. Oh my gosh, and there we go. So we're already very close to, if we take a curve, plug in our points, there's our base curve for the Gramatio and Kohler thing, right? We get a bunch of points in space, and we get them to create a curve. So points to curve, and there's, let's say that's our wall. Then the other thing is we have to look at this, and we have the bottom line, but it's actually shifting. So when this thing is out, the top goes in. When the top is out, the bottom goes in. So what we're doing is essentially like a negative copy of this curve. Okay, and so you ask yourself, like, how do you make that? Well, mathematically, what we'd probably do is take that and construct the negative of it. So let's test that hypothesis here. So I've got another set of points and another curve is generated by them, and let's just take y and let's do negative y. That's my hypothesis. That's what I think. And that's pretty good, but you see how it's actually flipped on the axis. So that doesn't seem to help too much. And so I could experiment with this a little bit, and I could say something like, you could say maybe it's always like 10 minus y. Okay, that gives us that flip, but it's still not aligned with the bottom of it. But 10's pretty close. And so I could kind of go back and forth and kind of experiment until I figure it out. But I want this to be parametric too. And I'm thinking actually that when I multiply this value, like when this is so narrow, it's like here. And the more that I multiply it, the further out this value goes. And so it seemed like actually what I want to do is basically subtract y from this value. Let's try that. So I do subtraction, and I'll plug in this value, and y in this case is this value, and that gives me kind of an opposite value. And then let's undo our math here. We don't want to mess things up. No math, and plug this in for y now. Oh man, and there you go. Okay, so we kind of experimented with this a little bit, but that's pretty sound. So the multiplier is actually what's affecting it. So we subtract the output here. We're subtracting the output from the multiplier, and that's actually giving us the negative curve. So that's what this other curve is. Let's go ahead and hide this. Okay, we've got that. Then what we need to do though is we need to get the wall height. And you could say, well, I can move this curve. But remember, one of the other things I showed you, I think it was the third week, you can just change the z value of the points you have. Right? Just change the number. So let's put in a number slider with a value range of like 0 to 20, and we'll call this wall height. And I think that makes more sense to do it that way. It's more parametric. Oh, there you go. So I have two curves. And when you have two curves, you can make a surface, right? You can have any more than two curves, make a loft. So let's do the bottom one first, and then let's shift click and do the top one. And we have a surface. So success, we got a surface. And we had a method that took a surface and that created this brick wall. Okay. Let's take a step back. To make that wall, we generated some numbers using the patterns we know to get points. We used the points to get curves, and the curves to get a surface. Okay, so from the bottom up. Okay, and then in this other method, we went from the surface to curves to points, and then we distributed the geometry. Okay, this isn't always the way that this thing works out. But I just want to demonstrate again the sort of like mutability of this as you traverse the, the model, the topological construction of the model. So we have our surface, and now we're gonna marry it to the contours, and then unhide. Oh, whoa! So now we have to go back and make some adjustments here. Like these are way off here. Let's see here. Yeah. Okay, so let's see. And in fact, let's see. So I got the number of bricks. It looks like varying it in the X is okay. Oh, I see. I think our wall's too small. So let's go ahead and increase the spacing. Or increase the number. Well, increase the spacing. No. The wall's okay. I think we need to go in and let's see. We need more bricks. Yeah, there we go. Okay, more bricks. Maybe a lot more bricks. And let's play with this size of the brick. I think the proportions are what are off. Let's look at so. Yeah, the box is actually longer in the Y than in the Z, so that's kind of messed up. And I also think that we want to make the contours smaller. We need more bricks in our wall. That's better. Okay. So we've got smaller Z, and then let's go ahead and actually let's say the brick has a long side, and the brick has the Z is going to be the same proportion as the Y. Like that seems to make there. That's better. Okay. So the brick is as wide as it is tall, but then it's actually longer than that. And we can set up a proportion, so we could say like the brick is 3 times as long as it is high. We could do that. Okay. If we play with this, we get back to what we wanted to make in the first place. Okay. Pretty close, pretty good. So we kind of like deconstructed a method here, and we were able to come through and create a parametric system that allows us to sort of play with this form. Okay, and it's in a parametric system. It involves a lot of play. You don't always know like how the system is supposed to work when you first start making it. You kind of iteratively refine it, and you play with the sliders until you get a setting that you want. And when you find that you have relationships between things, then you can kind of build those in. You can kind of program those in. So I could say something like the length of the brick should be 2.5 times the height. I could do that. I could do multiplication, and I could break out this thing and say 2.5. and actually I just said it explicitly. Let's extract a parameter, and let's just call this 2.5, so I can see what that's supposed to be. Okay, good. And let's plug in the z, and the output is like 0.75. Yep, close enough. And so now the height basically determines that proportion. That actually seems to have broken it, so that might not even be a good, but that's an idea. If you know that you want to codify a rule like that, you kind of wait, further in the process. I think we want the length to be something that you can play with. So I'm gonna go ahead and leave that. Anyway, so you iteratively refine it based on this kind of play, okay? You really don't know until you actually play with the system what you want. So we've got this structure, this basic idea, and like we made this form, but now it's variable. Like we started with the Grammantio and Kohler idea, but now we could do it with different shapes, like a parabola that's inverted. Let me go ahead and hide my loft here. And actually, let's play the spacing a little more. Very small differences in spacing make a big difference here. My parabola wall could go through, and I could change this slider to Bezier wall. So it kind of twists. You could also do a pattern where instead of doing this complicated kind of mathy thing that I did with shifting the opposite, you could set up a system where you had two curves, one controlling the top and one controlling the bottom, so that you could get more interaction, with the form of the wall. So I can go through and I could say, I want a spline. Actually, I'm going to go through and hide this quick. This is the performance of my computer starting to take a hit here. So I'm going to go back and just play with the loft level to visualize it. So I could do from a spline, from a sine curve to a parabola that morphs. So if I go back and turn on my bricks again, look at that. That's kind of cool. Kind of like that. So just like the example that we looked at. So this is how I designed the example that I gave you. Very much like the step-by-step process I took. I did some things and they didn't work out, so I made some different decisions. I started by looking at the problem based on the things that I knew, and I used the sliders to figure out what the proportions were to make it work. Along the way, I tried to make it as smart as I could. For instance, by figuring out that the box height should be related to the size of to the distance between the contours. Okay, so this is one example of this parametric design process. And when I'm done with it, I have this tool. I've made a tool for myself that I could use, and I could apply this to any arbitrary surface that I create, or I could generate a surface in Grasshopper. So it's a very flexible way of working. Okay. And when you're done with this, like again, you could bake this and you could export it to another program. You could do Make 2D to get the lines from it, to add it to one of your CAD drawings. It doesn't have to stay in Rhino for it to be useful for you, okay? Grasshopper, is useful because it really automates a lot of these processes for us and allows us to work very quickly. But then when you're done with it, you can always work in it. These will even export to Revit, okay? And you can add this to your design as a family, okay? So this stuff is really useful down the road. It's not just, we're not just playing around, okay? So this is a example. I just want you to like look at this and think about this idea of, you know, the sort of like process of, you know, like topography, you know, 3D like topology, points to curves to surfaces, and then backwards, surfaces to curves to points. And once you have that, it's just about distribution and transformation. Okay, so let's stop there, and we'll pick it up next time in lab.